today is honestly largely going to be about jargon for the stuff that we are going to be covering for the remainder of the class. Okay? So we are going to start our section on three-phase power topics today. And there are very specific ways that electrical engineers reference parts of three-phase systems. And so that's what we're going to focus on today. Because if we don't clear this up now, I'm going to be repeating myself every day for the next 2 weeks. And to be very blunt about it, that infuriates me. So I'd rather just take care of it today. So let's begin with our introduction. The right color here. Introduction to three-phase circuits. I'm going to use this symbol phi fairly regularly to represent the word phase. Okay. So in most industrialized countries, electrical distribution from utilities to connect to consumers occurs using a three-phase distribution system. All right. So to this point in this class, we have talked mostly about single-phase systems, or systems that we could consider to be a single-phase system. So a very simplistic representation of a single-phase system would look something like this. We have a sinusoidal source that we can represent using the following voltage, where VP in this case is going to represent what I'm going to call a phase voltage, and it will be an RMS quantity. Okay. 99.9% of all of the voltages that we're going to reference for the remainder of the class will be considered RMS voltages. Our source is connected to a set of transmission lines. I am representing these transmission lines as simply wires right now, but they may have some associated impedance, which we will deal with a little later. And those transmission lines allow us to connect our source to our load, such that we can divide this system into three distinct parts. So on the left-hand side, we have our source. On the right-hand side, we have our load. And in the middle, we have transmission lines. I'm going to call this wire up at the top hot wire, which is effectively how we send power from the source to the load. And then the return path here, if I could spell correctly, I'm going to call the neutral wire. Okay. So I want to point something out that I'm going to be doing continuously for the remainder of this class. anytime I have terminals, voltages, whatever, associated with the source side of our system, I'm going to use lowercase subscripts. So lowercase a and lowercase n in this case. Anytime I'm talking about the load side of our system, I'm going to use uppercase subscripts. So capital A and capital N in this case. Okay. So for this simple representation of a single phase circuit, it takes two wires, a hot wire and a neutral wire, to deliver some amount of power from our source to our load. Now let's look at a three-phase system. Excuse me. So in a three-phase system, we might have something that looks like this. So this is our source side. So I'm going to call this lowercase a, this terminal lowercase b, and this terminal lowercase c. I'm going to call this voltage VPA with an angle of theta A. This voltage will be VPB with an angle of theta B. And this voltage will be VPC with an angle of theta C. On the right-hand side, I'm going to have my load terminal. So I'm going to call this uppercase A, uppercase B, and uppercase C. And we might have something, excuse me, like this. I'm going to call this the LA, the LB, the LC, and again, we are going to connect our source side to our load side using transmission lines. Where I'm going to call this guy up here the A phase wire. In the middle, our B phase wire. And finally down here, our C phase wire. So we have source, load, and transmission lines. Again. Now, this particular type of system is called a three-phase, three-wire system. 3phi-3. We could also have three-phase four-wire systems and things like that. But I want to talk about this one specifically, okay? Because it tells us a lot about why we utilize three-phase power for distribution in most industrialized areas. So in our single-phase system, it takes two wires to deliver a fixed amount of power from our source to our load. Well, in a three-phase, three-wire system, it takes 1.5 times as many wires, because there's 3 transmission lines, to deliver 3 times as much power from the source to our load. So it is much more economically feasible to utilize three-phase power for distribution for this reason. We can either deliver more power using fewer wires, or we can deliver the same amount of power using smaller wires, which are inherently cheaper. So either way, economically speaking, it is a better option for us to use a three-phase distribution system. Now, you may be asking yourself, well, if it's cheaper to use three-phase, why don't we use 6-phase or 8-phase or 12-phase or something like that? And some places do, absolutely. There are even some places here in the United States that use higher than three-phase power. Those are typically metal refinery plants. And the reason that they use more than 3 phases is to make it economical to generate enough current in order to melt down metals. For the overwhelming majority of applications, the sweet spot versus simplicity and economic feasibility lies in a three-phase distribution system. Another very, very important reason that three-phase distribution is used is the application of energizing induction motors. Okay. So in a three-phase system, as we'll find out in a little bit, we are able to generate a rotating magnetic field of a constant amplitude. So if we have a rotating magnetic field with a constant amplitude, what we find is that we have a constant rotational torque when applied to a three-phase motor, which means that the amount of power that's delivered to a three-phase motor is effectively constant, or at least the amount of average power that's still delivered to a three-phase motor is effectively constant, which in turn means that the machine will experience the least amount of vibrations and therefore undergo the least amount of mechanical strain and wear and tear when it's served by a three-phase system. Okay? It's kind of intuitively obvious why a single-phase AC motor doesn't perform particularly well. And it's because as the voltage goes up and down, the motor is constantly speeding up and slowing down, speeding up and slowing down. We'll find with a three-phase system, it just runs at a fixed speed. Okay, so that's something that we're going to talk about in a little bit. Bradley.
So if there's like higher phase transmission lines, like they use in certain applications, are there also higher phase motors?
There absolutely are. And one thing, so getting a bit ahead of ourselves here, the way that induction motors work, typically speaking, they rotate at a frequency that is constant with respect to their excitation frequency. And so what I mean by that is for a 60 hertz system, typically speaking, an induction motor will run at some integer multiple of 3,600 RPM. because 60 hertz means that there are 3,600 revolutions in a minute, right? We can get away from this by introducing extra poles into the motor. So it's still going to be effectively fractional relations of that 3,600 hertz, and it's going to operate at a single speed. There are devices which are called variable frequency drives that enable motors to operate at different speeds. And what they do is literally convert a three-phase AC signal into a DC signal using what are called rectifiers, which you'll learn about in your electronics classes next year. And then they take that DC signal and effectively chop it up and make it look like a sinusoid at a different frequency. So anywhere from 45 hertz up to 100 hertz, and you can adjust what frequency that is depending on the settings of the inverter to allow motors to rotate at different speeds. There are lots of different reasons to do this. Some are to just prevent wear and tear on the startup of an electric machine. Effectively, when an electric machine starts to rotate, because the rotor is in what you would call a locked position, all of the internal inductances look like a short circuit. And so you see that its starting current is very, very large, typically 6 to 10 times larger than their rated current. So they experience a large surge of energy, which causes them to sort of jerk start, and then they smooth out to their normal speed. Well, with a variable frequency drive, you can start them off slow and continuously bring them up online to their speed without that herky jerkiness and all that kind of good stuff. That's kind of beyond the scope of this class, but it is a thing that happens. All right, so we have very basically talked about why we use three-phase distribution. Now let's talk about how we generate three-phase power very, very briefly here. So I'm going to attempt to draw a picture. It's going to be bad, but I will explain as best I can what's going on. I'm going to try to use, I don't want an ellipse. Force it to be a circle, I think. Great. So let's try to make this happen. Don't like that at all. Undo. Okay. Try this again. If it doesn't work this time, I'll just shittily draw one. That seems pretty decent. Okay. So I have drawn two concentric circles here, and what they are supposed to represent is what's called the stator of an electric generator. Okay. So the stator is effectively a stationary tube that contains coils of wire, which are electromagnets. Okay. So I'm going to try to represent a coil right here, and then a coil directly opposite that. And then let's say we're having a coil over here, and then another coil directly opposite that, and then a coil over here, and a coil directly opposite that. And I'm going to make this one blue. take that back. I'm going to make that one black. What I'm literally trying to do is make it match the three-phase panel over here with respects to phase so that I can remember what the order of the colors is. All right, so we have black, red, and blue, and then I'm going to color all the other ones in gray. We'll talk about them all in a moment. All right, so this guy right here represents the A phase. And this guy right here, I'm going to call A prime. Our blue coil represents the B phase, and the one directly opposite represents the B prime. And then our red coil represents the C phase, and the one directly opposite it is C prime. So these coils are going to have leads out to some terminals. Okay. So this is going to be terminal A. This is going to be terminal B. This is going to be terminal C. And the next thing that we are going to do is connect all of our primes together. I'm going to draw this, and then I'm going to try to jump over this guy. So I'm going to do the same thing on this side. And then I'm going to run this out here to the middle. That's going to be my neutral connection. So this is effectively a very simplified picture of how the stator is wired up. Now we're going to talk about the rotor. I am going to draw the rotor as if it were a permanent magnet, but in truth, it is an electromagnet as well. Okay. This black dot in the center here is effectively representing the axis of rotation. I'm going to call this top bit the north pole of this magnet, the bottom bit the south pole of this magnet. And I am going to attempt to indicate that our rotor is going to spin in a counterclockwise direction with an angular frequency of omega. Okay. So let's talk about physically what's happening in this system. How many of you guys have had physics 202? Almost all of you. Great. So arguably, you know generally what the term magnetic flux means. Okay. So for those of you who have not yet had physics 202, you need to do it over the summer, or you can't take circuits 3 in the fall. So just throwing that out there. But what's happening here is that when the north pole of our rotor is aligned with coil A is experiencing its largest amount of magnetic flux. And thanks to Faraday's law of induction, that means that the largest voltage between terminals A and terminals N is being induced. So we're going to have a voltage. I'm going to do this one in black. The positive polarity, black, is here. The negative polarity is here, and we're going to call this VAN. and it is a RMS phasor, or we can also look at it in a moment as a time domain voltage, okay? When our rotor spins, the magnetic flux seen in coil A is going to get smaller, while the magnetic flux observed by coil B is going to get larger because our rotor is spinning in a counterclockwise fashion. When the north pole of the rotor is lined up, sorry, I have two B primes here. My apologies. The one with the blue shouldn't have a prime. When the north pole of the rotor lines up with coil B, then the voltage VBN will be at its maximum value. All right. So I'm going to write that guy right here, and I'm going to do it in blue. And as the rotor continues to spin, eventually the north pole of the magnet will be lined up with coil C, which will in turn cause the voltage VCN to be at its maximum value. So graphically, what these voltages should look like as a function of time will be something like this. And I'm going to pre-apologize for my inability to draw sinusoids well. So this black curve is supposed to be representing VAN of t. Well, this will be VPA times the square root of 2 times the cosine of omega t volts. And then our blue curve that I'm going to superimpose on top of this guy should be something like this, where this is representing VBN as a function of time, or VPB times the square root of 2 cosine omega t minus 120 degrees. And our red curve should be VCN of t, VPC root 2 cosine omega t minus 240 degrees. Effectively, these three sinusoidal signals are just going to keep going up and going down, and the maximum flux observed in coil A will hit first. Then a little bit later, we'll see the maximum amount of flux hitting coil B, and then a little bit after that, the maximum amount of flux will hit coil C, and just repeat over and over and over. Okay. Now I've made an assumption here. That's because these things are supposed to be manufactured in this way, that the physical separation between the coil representing phase A and the coil representing phase B is 120 degrees apart along this circle. And then C is then 120 degrees away from B, and then A is 120 degrees away from C. So that we should observe that A, our voltage VAN, leads our voltage VBN by 120 degrees, which in turn leads our voltage VCN by 120 degrees, and then it just goes over and over and over, okay? So that's how we get exactly 120 degrees of phase separation between our signals, okay? This is what we are going to call a positive phase sequence. So in a positive phase sequence connection, A leads B by 120, which in turn leads C by 120 degrees. So for a positive phase sequence, we should have effectively 0 for our phase angle for VAN, and then VBN should be minus 120 degrees away from that, and then VCN should be minus 120 degrees away from VBN. If our rotor spun in the opposite direction, we would have what's called a negative phase sequence. The only change that we would observe is that these negative signs would change to positive, because then we would see that C is leading A, which is in turn leading B. So it'll just go the other direction around. Okay? All positive phase sequence and negative phase sequence means is the rotor is spinning counterclockwise or the rotor is spinning clockwise. It has no other effect on any of the analysis that we are going to do whatsoever. So in this class, all of our analyses will be using a positive phase sequence system so that we're consistent with the way that we represent our phase angles for all of our signals. Okay. So just want to make you aware, negative phase sequence does exist. It does not change the analysis in any way, shape, or form. We are just going to use this set of voltages to be consistent. Okay, so we have talked about where these negative 20 and negative 40 degrees, negative 240 degrees come from. Now let's talk about something else here real quick. If coil A, coil B, and coil C are made from the same material, so copper wire, having the same dimensions so that they have the same resistance, inductance, and all that kind of good stuff, and there are the same number of turns in each of those coils, VPA, VPB, and VPC will be identical values. So if the coils are identical, the voltage induced across the coils must also be identical. So what that means is that if a three-phase voltage source like this, like a three-phase generator, is manufactured correctly, the magnitude of the voltages should be exactly the same. And then the B phase should lag the A phase by 120 degrees, and the C phase should lag the B phase by 120 degrees. Effectively, we will have a balanced three-phase source. We'll talk more about that a little bit. Okay? Any potential hard part of analyzing a three-phase system is going to occur when the system becomes unbalanced. The source is practically never the location of that unbalancing because of the way that they're manufactured. Okay? The only way to unbalance a source would be to literally manufacture the coil incorrectly or physically place the coils not 120 degrees apart. Okay. So for all intents and purposes, we are always going to have a balanced source in our system. Okay. I'm sorry, what was that question?
Does that mean that unbalance would come from the fascias caused by transmission lines?
So it could come from transmission lines, it could come from the load. It just depends on what's connected and how it's connected and all that kind of good stuff. But it never comes from the source. All right, so all right, so we've talked a bit about three-phase voltage generation here. Now we are going to talk about the two different ways that sources can be configured to generate this balanced set of three-phase voltages. Okay. So source configurations. The first one that we are going to talk about is the Y connected source. So we will see this sometimes written out as WYE. Other times you may see it written as literally just the letter capital Y. And there are two ways that these are represented in schematic diagrams. I'm first going to introduce the conventional way, which I hate. And then I'm going to introduce the newer methodology, which I much prefer. Okay. So this is the way I don't care for. All right. It is literally looks like the letter Y, which is kind of obviously why we call it a Y connected source. And all of our phase voltages are measured between their terminal and this neutral conductor. So this would be an RMS phasor voltage, VAN, because it's measured between the A terminal and the neutral terminal. All right. I'm using lowercase subscripts to indicate that we're talking about the source side of the system. This would be our voltage, VBN. And this would be our voltage, VCN. Okay. This neutral conductor is optional. We will talk about why it is optional a little bit later. Bradley, what was your question?
Sorry, sir. I wanted to ask about VCN with the poles.
Oh, I have them backwards. You're correct. Yeah, they should match. Positive polarity on bottom, negative polarity on top. Thank you for catching that. Yeah, nope, that was all me, not. All right, so this is the conventional representation. My problem with it, for the most part, is that it's just a pain in the ass to draw. So how I prefer to represent a Y-connected source is something like this. Here's A. Here's B. Here's C. Here's N. So this is our voltage VAN, VBN, VCN. And I want to talk to you about something very brief here. Okay. The double subscript notation that I'm using, I know I talked about this very, very briefly at the beginning of Engineering 221 for those of you that had me. When using this double subscript notation, the first letter in the subscript references the positive polarity terminal, and the second letter in the subscript represents the negative polarity terminal of the element in question. So VAN is the difference between terminal A and terminal N. It's representing the exact same information as the drawing on the left, but to me, it's a little more simplified in how we can approach it. Okay? It's definitely easier for me to draw. You can do whichever one that you want to do when representing your circuits, however you want to do it, it's fine by me. Just know that I'm consistently going to use this guy over here on the right. So we can identify several very important parameters of interest for this Y-connected source. And this is where our lesson on jargon largely begins. Okay. So the first thing that we are going to talk about are our phase voltages. So what a phase voltage represents is the voltage drop over one phase of a source or a load. So in this circuit, our phase voltages are VAN, VBN, and VCN. So it's effectively just the voltage drop over each source that makes up our three-phase voltage source. There are also what are called line voltages. Line voltages measure the voltage drop between transmission line terminals of a source or load. Okay. So what I mean is if we measured the potential difference between transmission line terminal A and transmission line terminal B, we would have a line voltage. If we measure it between A and N, we have a phase voltage, okay? So I'm going to represent our line voltages in green. So here's one line voltage, VAB. Here's another line voltage, VBC. And our third line voltage is typically measured from C to A, VCA, like so. And we could draw these on our other diagram as well. So here's AB. Here's BC. and out here is CA. Sorry, it should be BC and BCA. So thus far, we've talked about our 3 phase voltages for our Y-connected source and our 3 line voltages for our Y-connected source. Another quantity of interest is the phase current. A phase current is simply current flowing through one phase of a source or load. Okay. I'm going to do these in blue. And I particularly define my phase current as flowing into the positive polarity terminal and out of the negative polarity terminal. So I will have phase currents IAN, IBN, and ICN, like so. Now, we have phase voltages and line voltages. We've talked about phase currents. We can't, there is a quantity called a line current, but we can't yet talk about line currents. And the reason for that is because line currents represent the current flowing through the transmission line. Well, if we don't have our source connected to something via transmission lines, line currents as a concept do not exist, okay? So we will introduce those once we actually start looking at full systems where we've connected a source to a load. Okay. So these are our quantities. I'll write these down. IAN, IBN, I. Okay. And so hopefully everything should be pretty easy breezy right now. Time to mess things up, as always. Yes, sir. So I'm not particularly sure about that unless they are representing some portion. So one way you, or reason you might see inductors in series with these voltage sources would be because since it is part of a rotating electric machine, they are going to have a practical voltage source representation to account for any internal impedance as well, right? So we could, if we wanted to be much more formal about this, put an impedance ZC here, ZB here, and ZA here. That's the only real reason that I could see that you would have some sort of inductance there. Now, I don't know, pardon? Yeah. Yeah, I'm not I'm not entirely sure. Send me a link or something and I'll have a look at it. Now I know in textbooks and all that kind of stuff, this is fairly straightforward, representing the voltage source by voltage source. Okay, so yeah, I mean, you can absolutely introduce 90-degree phase shifts using inductors and capacitors. Like that's how you can turn a single phase system into effectively a 4-phase system. So if you have a single phase system and then you tap the voltage and like put a capacitor in parallel with it, that introduces a 90-degree phase shift. Then you reverse the polarity of the voltage, that introduces an 180 degrees phase shift. And then if you put an inductor in parallel with it, that's going to introduce a 90-degree phase shift as well. That's more so for like a poor man's way to effectively make a single phase system behave like not a single phase system, much more so than actually generating voltages that are out of phase. All right. So this is our Y connected source. Now let's talk about a delta connection. Again, there are two different ways that these are represented. One I care for, the other I do not, because I am picky. So let's start with the one that I don't care for again. All right, so this is the representation of a delta connected source that I don't care for. And again, it's largely because it's a pain in the ass to draw this. It's called a delta connected source because they're connected in a triangle or delta shape. Engineers are usually pretty lame and boring when it comes to naming stuff. Now, how we can represent this in a way that to me is a bit more straightforward would be something like this. So let's take this as my A phase, this is my B, and this is my C. So between the A and B terminals, I'm going to have my voltage VAB. Between my B and C terminals, I'm going to have my voltage VBC. And between my C and A terminals, I'm going to have my voltage VCA. So this is how I prefer to represent a delta connected source. The definitions for phase voltages and line voltages will not change. So all I want us to do here is identify our phase voltage. Remembering that a phase voltage is simply the voltage drop over each source in our system. So what should my phase voltages be? Exactly right, VAB VBC and VCA. What about my line voltages? So line voltages are simply the voltages measured between the transmission line terminals. Any thoughts? They're going to be exactly identical. VAB, VBC, and VCA. So just to spell these out. Literally the exact same quantities. So this is where things get a little wonkier, a little more difficult, right? For a Y-connected source, our phase voltages and our line voltages represent different quantities. For a delta connected source, our phase voltages and line voltages represent the same quantity. Okay? So this is why things can tend to get a little bit confusing. What we will observe once we actually connect things here is that for delta connected things, line voltages and phase voltages are the same. And for Y connected things, line currents and phase currents represent the same thing. So there is a duality here. All right, so our phase currents I believe I did in blue. So they're going to represent the currents flowing through our sources, positive polarity first. So this is IAB, IBC, ICA. Like so. So, sorry, let me make sure that that looks like BC. So the question is, would that mean that IAB and IBC are equal to each other? And the short answer is it depends on a number of factors and also explicitly by what you mean, okay? So in this case where we have literally no connection or whatever, sure. Because the current has nowhere else to flow but in that triangular path. And we don't have any impedance anywhere to cause any changes, okay? Once we start connecting things though, that all goes straight to hell, right? Once we no longer have open circuit terminals here, what we'll see is that we can apply Kirchhoff's current law at each one of these transmission line terminals and develop relationships for how things split off, but we cannot succinctly say that, oh, they're all equal or anything like that. So that is exactly why I'm defining everything like this, so that we always, as our baseline calculation, we're always determining the absorbed power for everything that we're going to be dealing with. once we get to three-phase power. That is exactly why I have chosen the current to flow into the positive polarity terminals. All right, so we've talked about our two sources for three-phase systems. Now let's talk about our two options for connecting loads. They're the exact same two options. We can have a Y-connected load or a delta-connected load. So a Y load can look something like this. Where I'm going to call this ZYA, this guy ZYB, this guy ZYC. We may have a neutral connection, so I'll have capital N there. Another way to represent this would be this guy. So here's ZYA, ZYB, ZYC, where this is terminal A, B, C. So our phase voltages are going to be the voltage drops over each phase or each part of our three-phase load, right? So that might be something like this, DAN, where I'm using capital subscripts, BN, and CN. Let me draw them on our other representation. Like so. For our line voltages, that's just going to be the drops over our transmission line. Here we have VAB. Here to here, we have BC. Here to here, we have CA. On this side, like this. And lastly, oh, I should write those down. And lastly, we will have our phase currents. Here's IAN, IBN, ICN. Or in this representation, AN, BN, CN. And there is our Y connected load. Our last thing to do then is to introduce our delta connected load. So here's terminal A, B, we'll have something like this. I'm going to call this Z delta A. This guy is Z delta B. This guy is Z delta C. The other way to represent them something like this. And my hand is getting very tired here, so I'm going to take a very quick break. Effectively, what we are going to see is that the phase voltages, line voltages, and phase currents are exactly the same thing as we saw in a delta connected source, except that we are going to have uppercase subscripts because we are on the load side of the circuit. Okay. So actually, our phase voltage, there's VAB. Here's VBC. Here's VCA. Our line voltages are the same quantities. And lastly, our currents. Like so. All right. So we have effectively just 4 different permutations that we could possibly ever have to analyze. Okay, we're considering a single source and a single load. We can have a Y-Y system in which the source is Y connected and the load is Y connected. We can have a Y delta system where the source is Y connected and the load is delta connected. We can have a delta Y system where the source is delta connected and the load is Y connected. Or we could have a delta delta system in which the source is connected in delta and the load is connected in delta. Okay, there's just 4 different combinations. What we are going to do on Wednesday is we are going to begin our analysis by looking at Y-Y systems. And we are going to do this specifically looking at what is called a balanced Y system. And we'll talk about what exactly it means for a system to be balanced and all that kind of good stuff, okay? Once we have analyzed our balanced Y system, we are then going to learn a series of transformations that will allow us to represent any source combination as a Y-connected source and any load combination as a Y-connected load, so that we can effectively apply our YY analysis techniques to the three other types that we have. And the reason for this is we will find that the analysis of a YY system, especially a balanced YY system, is very easy. And the analysis directly of all of the other systems is a pain in the ass. And so I wanted to show you how to do it in the most quick and efficient way possible. So that's what we've got coming up on Wednesday. We'll go through a rather lengthy discussion of what exactly a balanced system entails and what that allows us to do. And then we'll get into those transformations. Yes, sir. Somebody in Zoom said something. All right. Scroll back up to the Y load. Sure.